and many of these organic compounds are present in the air, present in water, present in solid waste. So, if you want to determine these compounds in the environment, this is how we go about doing it. If there is methanol or something like that, you must get a peak corresponding to sigma to sigma star and n to sigma star, because there are no double bonds. So, like that, if it is an ethylene structure in a gaseous environment, then what do you do? Then I will show you this table. The first one is ethylene. It shows a peak at 171 nanometers and epsilon value is 15,530 and solvent is vapor. It is a, if it is there in the air, it has to be in the vapor form. So, similarly 1 octene, it has got a very high molecular weight, but it has got a 1 octene means 1 double bond between first and second carbon atoms, and a total octene means 8 carbon atoms. So, it shows a peak at 177 and lot of the single bonds, but only 1 double bond. So, the peak has shifted from 171 to 177 and epsilon value is 12,600. For typical this thing, for typical value it is a fairly strong band. That means, it shows a discernible peak if it is there in the air or in the liquid. Similarly, acetaldehyde not so good, because this corresponds to sigma star transition. So, 20,000 it is a strong one, but it is not in the purview of normal spectrophotometers, because the normal spectrophotometers operate between 180 to 1100 nanometers. So, this one, it also shows a peak at 190. As I told you, 180 is the minimum, 190 it should show a peak, but it has got a very low molar absorptivity, only 17. So, it will not be visible. So, same thing is true with acetone, 166, not good, but it is in vacuum region, not seen in the spectrophotometer. 189, yes, it is around 900, fairly very near the limit. So, you will definitely see a small peak or a hump. If it is acetic acid, you know that acetic acid is soluble in water, and it shows a peak at 208 nanometers, and this has got 32 only. So, this corresponds to sigma star or n to sigma star, because acetic sigma to sigma star are normally not shown. 208 if it shows a peak, and if it is a very weak peak, it has to, with only 32 molar absorptivity, what you will conclude is it has to be an n to pi star. The electrons on the oxygen should get excited to sigma star. N to sigma star is only 32, but this it shows another peak 220 and 100 epsilon, not a very good peak, but butyl nitrate it shows 270 and 17,000, excellent one. 270 another one, another peak around almost at the same level with 14,000 first. So, it is some sort of a doublet in butyl acetate. So, what do we conclude from this table? That is, same compounds in vapor form, neat form. Neat form means in the without any solvent. Vapor form means the substance in a vapor or in different solvents. I can dissolve a substance in different solvents and find out the absorption spectra. So, the same compound in each form there will be a slight difference in vapor form or neat form or different solvents. I have shown you here previously in the previous slide. This is 270 17,000 ethanol and 270 and 14,500 in hexane. Here the difference is between the molar absorptivity. Solvents are different, same substance and wavelength is same. In acetic acid it is 208 and 220, ethanol and hexane are the solvents, sometimes vapor, sometimes heptane, like that. That is the conclusion from this, same compounds in the vapor form. neat form or in different solvents show absorption maxima at different wavelengths, and then solvent effects are particularly severe for weak absorption bands. That means, if you, as far as possible, you should take a spectrum with neat form without any diluent. Sometimes weak bands disappear if you do it in solvents, more polar solvents, and same chromophoric group, same substance with a functional group can show different wavelength, but the same peak, that is n to pi star or pi to pi star in similar same chromophoric group in similar compounds, that is in aldehydes, it shows different peaks depending upon the molecular weight and molecular cross section that we have already discussed in the previous slides, that is minus dp by dt is equal to 1/3 of g into n is that number Avogadro's number, etc., where maximum is 10⁵. So, for all compounds the lambda max will be different, and molar absorptivity also will be different, but the chromophoric group may be same. What is a chromophoric group? A chromophoric group is a functional group like alcohol, aldehyde, ketone, amine, and then many other compounds like that are acids, they are known as chromophoric groups, and these compounds can be present in different compounds with different molecular weights, but the absorption peak what they show should only correspond to n to pi star and sigma n to sigma star. So, if the molecular weight differs, the same chromophoric group will show you different peak. So, the your possibility of finding different organic compounds in a given matrix always increases. That is the beauty of spectrophotometry, especially in the environmental monitoring with respect to pollutants. So, these conclusions are very important. I expect you to remember all this, and it will be useful for your tests also. Now, another lesson we learn is an isolated functional group not in conjugation with any other group is called a chromophore. This is the definition. So, I have already explained to you aldehydes, ketones, acids, these are all functional groups, but these functional groups should not be in conjugation with any other group, that means not separated by a single bond and another functional group. Okay. So, functional groups that do not show a character, and I come to the middle point now, I am talking about it. Functional groups that do not show a characteristic peak above 200 nanometer, but when attached to a chromophoric group, it can cause a shift to longer wavelengths and increase in intensity also. That means, if there are two functional groups, then they may add a little bit to the peak and push it to the right. Instead of 200, it may show you a peak around 210, maybe 205, maybe 220, but it is a characteristic peak corresponding to particular transition, but influenced by another functional group. So, such functional groups are called as auxochromes. These for example, these OH, NH2, SH, the mercaptans, halogens, all these things will show you a peak which should appear at longer wavelengths, but on their own these things do not show a peak. If there is a CH3OH for example, you will not get a functional, you will not get a peak for OH, but if it is there in a diene or something like that, it can push the peak towards the right. That is the beauty of these auxochromes. Now, there are, coming back to the Woodward-Pfizer rules, for acids and esters there is a possibility that again these things can be empirically correlated. How do we do that? Is when we have beta monosubstituted substances, that means from the second carbon atom from the functional group, that is alpha beta unsaturated, no, CH2 double bond CH single double bond CH, like that, If there is a substituent on beta carbon atom, then the base value is 208, and alpha beta or beta beta disubstituted substances, the peak will be at 253 nanometer base peak. Always remember the numbers what I am giving you are base peaks, and remaining are the addendums, something like addendums, and alpha beta or beta beta disubstituted will give you a peak at 253, and alpha beta and beta disubstituted 214. Extended double bond, as usual it gives you 30 nanometers straight away, it pushes the lambda max by 30 nanometers. Exocyclic as usual, that is a double bond attached to a ring from outside. Double bond is attached to a ring outside, that is 5 nanometers it will push. Endocyclic double bond is also going to give you another 5 nanometers, that but it has to be in 5 or 7 membered ring. Gamma or delta substituted alkyl groups can push the lambda max by about 18 nanometers. That means a carbon atom from the double bond you start counting alpha, beta, gamma, delta like that. As you go away, it can push the lambda max by 18 units, but remember all these things need to be connected by a single bond double bond structure, that is conjugation. If there is no conjugation, the effect could be nil, you have to remember that. Okay. So, here is another example I have shown you, tried to show you here. This is the double bond, single bond, double bond, single bond, double bond. Okay. This is CRO, R may be, if R is a hydrogen, then it is CHO, aldehyde. So, parent compound is aldehyde in this case, and lambda max is 210 nanometers. If the parent compound is a ketone, that means if this double bond is somewhere on alpha position with oxygen where alpha is written and all others alkyl groups, then the base value would be 215 nanometers. Okay. And if it is alpha substituent, for assuming that CHO is the functional group, next carbon atom is alpha, next is beta, then next here is gamma, one more carbon atom delta, and this carbon atom is also gamma with respect to this carbon atom. So, alpha, beta, gamma. If it is functional group, this is the functional group, alpha, this is alpha, this is beta, this is gamma, this is gamma. If the line extends, it is delta. So, every alpha substituent, as you can see here, it adds by 10 nanometer, it pushes the peak by 10 nanometers, beta substituent by 12, exocyclic ring as usual it is 5, and carbon oxygen and carbon double bond in 5 membered ring, it will contract, it will increase the required energy. So, the peak will be pushed on the left side by 10 nanometers, and only carbon in 5 membered ring is 5. Enolic OH or alpha substituent, here wherever if there is an OH group here in alpha and beta positions, this is beta, and if there is an OH group, you can see the jump, it is maximum 35 nanometers, because all the hydrogens can be in conjugation again. So, it effectively increases the conjugation, thereby reducing the energy required for transition from the N to sigma star or pi to pi star. So, alpha chloro group, it gives you 15, beta chromo group gives you about 23 nanometers, it pushes the lambda max. So far we have discussed about the aliphatic carbon atom, not one of them is aromatic. Now, aromatic systems, do they conform to this kind of rule? That is the question. Quite often we see that there are number of peaks even in aromatic compounds in ultraviolet region, and we are not discussing about infrared or FAR IR, etc., NMR, etc. in this thing, because for normal pollution control course we come across these compounds in the environment. So, there is no question of determining the structure or something like that. Our aim is to identify different organic compounds present in the air or water or in solid waste. So, if there are aromatic compounds in the environment, as there are, whichever environment you take, nowadays we see lot of aromatic compounds, including the camphor what you burn in your this thing, etc. Many of them are aromatic compounds, they will all be there in the air. So, in your day to day organic requirement of your organic compounds, you will come across many times phenols, floor cleaning chemicals, water cleaning chemicals, paints and sprays, room sprays and many of these things, attars and room freshener, body freshener, they give an advertisement that India fog se chalta hai, fog India mein kya chalta hai, fog chalta hai, all those things contain organic compounds which are aromatic in nature. Many of the food materials, they contain benzene, benzoic acid, and many of them are used as food preservatives. So, all of them, do they, if they are present in the environment, do they show some sort of peaks in the UV visible range? That is the question. The answer is yes, they do show certain peaks. For example, benzene and many other organic compounds show strong absorption bands at 184, 202 and a series of weak bands between 230 and 270 nanometers. These are associated obviously in benzene and aromatic structures, you will see only single bond, double bond structures. So, single bond can give only rise to say sigma to sigma star, they are all in vacuum ultraviolet range. So, all these peaks are attributed to pi star transitions. These fine structure bands are susceptible to solvents also. So, if it is a pure compound, you will get very sharp peak. If it is present in some solvent, it will show you a broad peak. That is another identification of whether a substance is pure or not pure. I will show you some of these figures later. See here, the bottom figure is in a solvent. See here, in the top you see a peak around 230 and then 240, somewhere around 242, 240, here it is 250, there is one peak, here there is one more peak, and between 255, 258, 259 there is one big peak which is shoulder, and one more peak at the around 259, like that it shows a peak. This is all UV range, ultraviolet range, from 180 to 350 it goes, but all aromatic compounds, as I was telling you, will show you number of peaks. This is the characteristic of aromatic compound. Any aromatic compound should show you this peak. So, it is like a pass fail test. So, if you see a structure something like this, we immediately say yes, it contains some sort of organic compound. Now, the same peak, if it is there present in a solvent, you see the structure of the peak, how it is coming. The peaks are almost same, but small disturbances, they are all leveled out here, and corresponding to this peak there is this peak, and these peaks are all wiped out, and corresponding to this there is one more peak pushed to the right, something like an auxochrome, and this peak has merged into one peak pushed slightly around here, and somewhere around 260 again that is also pushed. So, the top one is in the vapor form, the bottom one is in a solvent. So, in a solvent peaks look smarter, beautiful, but it does not actually represent the basic structure of the chemical. So, if you want to take a real look whether a substance is pure or not, you must always take it in the neat form without any solvents, and this is a perfect case to show. And this is for aromatic substances. So, again substitution helps a little bit. So, how does it help? An alkyl group shifts the lambda max to longer wavelengths. If there is any alkyl group in the benzene ring, you will see the same structure, but all peaks shifted to longer wavelength. This is known as bathochromic shift. Very important shift observed in many aromatic compounds, because 99% of the time we do not deal with benzene alone as a component or a constituent. It will always be substituted with some groups. Even the Dettol and other things what we have seen, what we use in day to day life, medical of hospitals etc., they all show you a peak shifted to longer wavelength, because it contains some alkyl groups present on the benzene ring, toluene, xylenes, all those compounds. So, if there is it is a second alkyl group, xylenes, it has got two alkyl groups at one may be at ortho, one may be at para, one may be at meta, that is adjacent, second adjacent, third adjacent. Third adjacent would be opposite, exactly opposite to the first one. So, again it produces a bathochromic effect with increased molar absorptivity. Similarly, an isomer, if it is the groups are attached to single carbon atom, then the shift is to shorter wavelengths. What I will do is I want to show you this kind of thing. So, if I have a benzene ring like this is a position alpha, second position, third position, fourth position. Okay. So, a substituent, this is ortho, and this is 1, 2, 3, 4, 5, 6 membered ring, and 1 and 2 is ortho, 1 and 3 is meta, and 1 and 4, if there is a substituent, then it is para. So, the 1 and 5 would be again meta only. And 1 and 6 is ortho again. So, if there are two groups on 1 and 2 position, in ortho position, two substituents, these represent crowding of the electronic structure between 1 and 2. So, this should increase repulsion between the electrons. So, it is not favored. So, it requires more energy to excite the electrons. So, it will push the peak, towards shorter wavelengths. Compared to this, 1 and 3 and 1 and 4, these push the electron, push the peak towards longer wavelengths. So, alkyl groups shift the lambda max to longer wavelengths, that is number 1, bathochromic shift. Addition of second alkyl group para produces bathochromic shift, increased epsilon, orthoisomer shifts to shorter wavelengths. This is understood now, I hope. So, more conjugation should shift it to longer wavelengths expected. So, suppose I have a group like this COOH, and here I have a single bond, double bond and single bond and again COOH group. So, this should shift the lambda max to longer wavelength. So, similarly NH2 and OH2 groups shift the epsilon and E and B bands. These are designated as E band and B band, R band, like that, and they shift to longer wavelengths, but they kill the fine structure which I had shown you earlier for benzene ring. because all of it will be n to pi star transitions, fine structure will go away. So, some effect of oxochromes I have listed here. For example, benzene E2, they are designated as E band and B band, and 203, 210, these are all sigma to sigma star, something like that, these are all n to pi star bands. So, you can see that the peaks are shifted and the lambda max keep on increasing with different functional groups, phenol, phenolate, aniline, aniline cation, anisole, thiophenol, etc., different compounds. But remember, all these compounds can be present in the environment, in the water, in the river, in the air, in the solid substances, like that. So, you can see that many of them are water soluble in the last table now, aqueous alkali, water, aqueous acid, methanol. Methanol is again miscible with water. It's like that, many of them are present in the environment. So, similarly, but this is the typical rule. Again, this is not empirical, this is again empirical. Okay. In the empirical this thing, what we say is X is equal to hydrogen, X is equal to OH or O alkyl. So, parent chromophore is X alkyl, alicyclic or ring residue. So, to that what I want to tell you is these are the substance. If there is an R alkyl group, it will add 3 at ortho, 3 at meta and 10 at para. Again it gives you a feel whether the substance is in the required group or not, whether it is shifting. Well, just by knowing the actual and pushed wavelength lambda max, you can say without doing any chemical analysis whether it is ortho meta or para, compound, unknown compound. Same thing is if it is R is equal to OH, OMe, that is oxygen containing compound, OH, OMe and O alkyl. This may be OCH3, this may be OC2H5 or something like that. Ortho meta is 7, but para is 25. Similarly, suppose the substituent is chloride, it does not shift if it is there in the ortho position. But at para, if the substituent is chloride is at para, then you can see that 10. Same thing is true with bromide, 2 and 15, amine is 58 compared to this thing, because amine is an electron releasing agent, because it has got 2 electrons, lone pair of electrons on NH2 group, which can participate in the conjugation of the benzene ring. Similarly, NHAC is 20, 20 and 45, and then NMe is 20, 20 and 85 N methyl groups. RO is again 11 and 20, that leads to approximately 78 nanometer, pushing wavelength to the right, that is towards longer wavelength. So, like that there are several things. For more details you should look into the textbooks and to gain an insight. I have tried to give you as much insight as possible with respect to the organic compounds in UV and visible region. What I would like you to do is in the next class is we will look at the structures and solve some problems where the peak is expected and where it is actually. So, that is in a way like testing the Woodward-Fieser rules, that we will do, and then we will move on to instrumentation and Beer-Lambert's law, etc. Thank you very much. Have a nice day.